Right, good morning, and well, hopefully you're awake after yesterday's dinner. Thanks for inviting me and giving me the possibility to talk. So I'm actually talking on behalf of the group of people, team who are working on this analysis. So I need to acknowledge David Schroeder from CIPOM University of Reading, Pablo, and you, Katya, and Julian. And this actually fits into 3 projects. That's why there are so many logos there. It's ACSIS, it's actually primarily UK ESM analysis, but also linked to ACSIS and also linked to the project APIA, which is UK-Germany joint change in Arctic Ocean program, and looks at the changes in Arctic physics and ecosystem. Now, try to go very quickly and through this outline, and probably skip some slides as well. So basically, I'm going to talk about the motivation why we are doing this, about methods, and then show some validation of the results from the model, and look at the future state of the Arctic Ocean in terms of circulation and sea ice, and now present the discussion and outlook. Something happens there. Okay, so motivation. This came from several angles. One angle which presented by Igor Polikov with the seminal paper in Science 2017, and he claimed from observation that Arctic is changing a lot and became more like North Atlantic. And reason for that, because of the North Atlantic inflow, which is continuation of the transatlantic drift, bringing salt and warm water into the primarily Farm Strait, then into Arctic proper. Second part of it, Andrew argued in his paper that if you do that, you change the state for the biogeochemistry, you precondition the nutrient supply, and Arctic becoming more like North Atlantic with the increased primary production, especially if you have a ice retreat and more light coming into the ocean, whereas North Atlantic is declining basically in terms of the primary production. And third one, we argued that basically if you remove sea ice, some difference, at least in the upper part of the ocean, can be moderated because of that. So we start some kind of hypothesis and try to see how this fits in the what we're getting from the model. So the first one came from the APIA project, and we thought about the fact, okay, if you look at the circulation in the previous rounds, especially high resolution projections, you see that there's change in the Arctic circulation, specifically connectivity between the Eurasian part of the Arctic and the Canadian part of the Arctic, which means flow across the Lomonosov Ridge is changing, and there's some kind of picture shows the geostrophic velocities or geostrophic actually currents through Montgomery potential at depths of 300 meters, and you can see that. Just probably try to go into here. So basically, it shows the quite strong anticyclonic circulation in the Eurasian part of the Canadian part of the Arctic, and cyclonic circulation in the Eurasian part of the Arctic. And the thing is, these two circulations are split basically; they are not communicating much. And the last part of the idea is how the longer ice-free season actually can affect the ocean, and specifically upper ocean. Right, so what we are doing, hopefully, yeah, it works. Right, so basically, we're looking at the UK ESM rounds, so not too many of them at the moment. So initially, we started looking 5 ensembles, and the SP1, basically the 4 projections for scenarios. For this presentation, I just focus on the one at the moment, and which is 8.5, around 179, I think. And we'll be comparing the data with the validation from the hydrographic data sets, and also fluxes through the straits, and with the sea ice information from the satellite and analysis. This is slide came across the NDU, had been shown several times. This is some kind of generic view on the ice concentrations in the Arctic and Antarctica for the period of 2000s, basically. And the main feature is basically the fact, yes, we got too much ice, it's sort of known. The seasonal cycle seems to be not too bad, at least for the Arctic. Antarctica is not great, but for the Arctic, we could sort of rely on this. Now, and if you look in a bit more detail, this is field of ice concentration for the longer period averages, 78 to 75. So left part, this is UK ESM, and the right part, this is the HUD SST. And we see, well, basically it's expect that winter sea ice, it seems to be okay, and which is mostly controlled by the atmosphere and ocean, to some extent actually ocean heat. But if you go into the sum, we clearly see the differences. You can see that model overestimates sea ice in terms of concentration and ice extent. If you look at the thicknesses, the situation is more dramatic. So left, it's UK ESM, right? This is the TriSat data courtesy of CIPOM UCL. And you can clearly see the model overestimates sea ice drastically, and specifically, it gives you your own pattern, basically. And one of these features, which I'll try to point with the mouse, this part, between the Siberian Sea, is very common for the low resolution models. It's practically everywhere. So if you run any cross-resolution models are getting this basically. But the main issue is this spread of the thickness, thick ice into the Central Arctic, which we don't see in the observations. Right, now I'm going to the oceanic fluxes and ice fluxes. So I just remind you, if you don't know where the straits are. So this is the Fram Strait over here, 17,829 north. Mostly chosen because Alfred Wegener Institute had a very long time series of the moorings there since 1987. So next bit is Barents Sea opening, so-called Barents Sea opening. This is run by Norwegians, and again, it's quite a long time series, about 18 east, and the Davis Strait run by University of Washington and Woods Hole basically together, and it's also quite substantial information there as well. Right, start from the sea ice, the courtesy of David Schroeder, who actually did this analysis. So David looked at this area, I think it was presented by Michelle as well, and what David did, he compared this sort of ensemble simulation of UKESM with the red curve. This came from the biomass reanalysis, not the data, it's reanalysis. This came from the University of Washington model by Zhang and Steele. And this red bit, it's Kreisat. So clearly, by all means, the model overestimates the ice thicknesses. The lower slide shows the fluxes of ice volume through the Fram Strait. Here, actually, model does not too bad. There's a bit of spikes in the observations, which not represented in the model exactly, but you can see this type of magnitude is not unacceptable in the model. If you look at the fluxes through the Fram Strait, the oceanic volume and then heat, salt fluxes. Again, this is long time series from the model. I didn't put any data here, but basically we know from the observation that roughly it's about 2.5 square of outflow, which correspond to the model quite well. The problem with the Fram Strait fluxes is a very huge uncertainty on the observations, plus minus 5 square drops. So basically, whatever you get in this range is right, more or less. For the salt fluxes, we are doing not too bad, out of roughly about 60 kilotons per second inflow of the salt into the Arctic Ocean, which is quite realistic. Freshwater. So, okay, this slide, top panel, blue line represents the model. There are 2 lines here from observation, black one and the magenta one. They came from different setup of the sensors, of the moorings. So the black one has less moorings than the magenta one. They didn't cover the shelf, the East Greenland shelf, and you can clearly see it impacts variability and trends. That's one of the issue observations. If you pick up a series, you say, this is great, this is what I'm going to do, this is complete absolute truth. No, it's not, right? So if you change the location of the sensors, you're actually getting different results in terms of variability and trends. Now, that we need to account all this. So if I put some kind of trends here, so model shows about minus 15 squared of trend per decade, and for the heat flux, we're getting warming of the Atlantic inflow into the Arctic Ocean. Davis Strait, not much excitement, except we know that the volume are actually not too bad, because the data from Pescari around this time, and they show this 2.2 squared of south, which is not too bad. And there's also data early from French around this time, and this one about 2.5 squared, which is completely correct. Freshwater, same, the value about roughly about 100 millisieverts is roughly correct. Barents opening, we're still doing this analysis. We know that inflow it's about 2.53 squared, which is again not too outrageous. I'll skip this one. So no, I shouldn't skip this one. So we also show that in the model we have a warming of the inflow through the Barents Sea about 11 terawatts per decade. Now, dynamics. The idea is to look at the dynamics and what we're using proxy of the sea surface height gradients and also barotropic function. This came actually not from UKESM, this is the wrong title here, unfortunately. This came from the OMIP simulations, which is the same mode of configuration, but forced with the reanalysis, basically. You can clearly see that the sea surface height gradients, the color bar here, and this fade green lines, which are barotropic stream functions, show very large coherence, basically. So you can see that practically using sea surface height, you can demonstrate give you a representation of barotropic flow. And the right side, this is the dynamic topography of the Kreisat, and you can see for the same period they match quite well. So model OMIP's doing not too bad. Now, if I jump into the UKESM, that's what we're getting into for 2040. So basically, just to show you difference between the cycle of present day climatology and the future, you can see the reduction of the buffer gyre, which is here, and also shift of the buffer gyre, and you can see much larger Atlantic inflow into the Canadian basin. If you go further to 1990s, you can see the same process happens again and again, basically. So practically we're losing Pacific water component in the Arctic Ocean altogether. If you compare, again, this is the present day sea surface height, to the temperature SST and also to the sea ice, you can see there's a quite strong correlation between the circulation and the inflow of the Atlantic water, which is right here. And again, we can see that very limited inflow of the surface Atlantic water actually keeps sea ice in the Eurasian basin. If you move a bit further into 2040, you can see a lot of correlation between enhanced inflow and the penetration of Atlantic water in the Arctic and the affects sea ice. You can see clearly that you have this ton of the open water emerging from the center anatroph. If you move further to 2090s, the same idea, more Atlantic water coming in, less sea ice, practically more sea ice, and that's end of story of sea ice.
10 minutes.
Thank you. Right. Summary. Well, basically, we started looking at the model validation, and model is not outrageously bad. There's clearly deficiencies and biases, mostly in terms of sea ice. In terms of the ocean, they're not doing too badly, interesting enough. We also look at the trends, and we need to still analyze the trends, but there's a clearly signal of the warming of the Atlantic inflow through the Fram Strait and Barents opening. We can see the shift of the circulation towards 1940s. Actually, starting from the 2040s, there's a very drastic change in the circulation from substantially pronounced wave to the very small wave and very large Atlantic anticyclonic flow. And basically, that's quite interesting because it's clearly coincide with the ice development or disappearance of sea ice. It's not necessarily cause, but they're definitely linked. What next? Analyzing the different water mass fluxes and pathways across the Lomonosov Ridge, looking at the geostrophic circulation, and analyzing also the exchanges to the greenhouse Scotland Ridge, because at the moment we are looking at the practically border between the Arctic and Nordic seas to some extent. It will be interesting to look at the observations, how the model performs in comparison to the observations across the Scotland Ridge. And I think I'm missing something. It's not there. Can't remember what it is. Anyway, right. Thank you.
Time for a couple of questions. Rowan at the
That was very interesting. It's slightly overwhelming amount of information.
Okay. Good. Not bad.
Can you just say a little bit more about what the projections are for the freshwater export from the Arctic into the Atlantic?
Well, I don't have the slide at the moment. We're working on this. So what I presented just climatology at the moment, the analysis of the current climate, sorry. There's no, in this talk, there's no projections for the freshwater. So I cannot answer this question. We don't know. You're still
so
not
have you looked at, I mean, you said
we're starting, yeah. Well, okay, right. In terms of discussion, yes, probably we could make some kind of a solution here. Let me check. Yeah, I think one thing which surfaced from this plot is the fact that the majority outflow happens through the Canadian Arctic, right? So Fram Strait sort of blocked. There's a very, very weak outflow here. It's basically, you can see these gradients between the blue and the red. So it's very weak outflow here. So most of the stuff will come out through the Canadian Arctic. And there will practically Pacific water plus rivers. They just go straight into Canadian Arctic. Currently part of it go into Canadian Arctic, like Narrow Strait or Lancaster Sound. Part will go through the transport from the Fram Strait. It's not the case anymore for 2090 or 2040. That's complete answer. In terms of the numbers, I don't know. We're starting looking at this, but there's no numbers at the moment.
Thank you. And Colin again.
When we were developing the physical model that underpins the system model, which is the Orca-1 configuration, we were often comparing it to the M216 Orca quarter physical model as well. And one of the key differences we saw was flow through the Fram Strait and the Denmark Straits. Yeah. But the Orca-1 model had problems with that. So I think it would be interesting for you to compare what you get here with the two physical model variants, the two Hypotheses 3 models at the two resolutions. Yeah. You might find some differences in flow through the various straits. Yeah. Order of degree, obviously, resolving things better. Yeah. Well, I agree. I mean, the main issue with the high resolution, because if you go to high resolution, potentially start resolving the boundary flows in the Fram Strait. So you have a West-Pisgah current represented better and East-Greenland current represented better. It's not necessary. It definitely will be better than 1 degree, but it's not necessarily good enough to produce the natural flows. I think we need, clearly I agree, we need comparison with the quarter degree, but we need actually, one thing we're going to do, we need to split between different components of the exchanges, looking at the northward flow, southward flow, just to see how they hash matching basically.
Okay. One more question at the back.
Could you briefly say about the change of ocean circulation?
So say again, please.
You talk about changing ocean circulation about
2040s. 2040s, you mean? Okay. I mean this one. Yep.
Sometime in the future.
Yeah. Okay. Okay. Right. So at the moment, I don't have the analysis of the circulation of the currents per se, but we're using sea surface height as a proxy for the barotropic circulation. That's a kind of argument. It comes from the fact that the density practically uniform in the Arctic Ocean beneath the mixed layer. So you can the sea surface height. It's a good proxy, some kind of zero-level proxy for the barotropic stream function. So basically, that's what we see. We saw the much stronger Atlantic inflow, and the Atlantic water, that's some kind of plot on the left, penetrates beyond Lomonosov and Makarov, Mendeleev Reach, from Makarov Basin into the Canada Basin. And the buffer gyre is shifted and it's smaller. I mean, some kind of more like cyclonic type of circulation, if you wish, which we occasionally experience in the Arctic Ocean during cyclonic periods. So then if you go into the 2090s, buffer gyre is practically destroyed. It's shifted. That's what it showed here, basically. It's shifted. You can see that, and it's much smaller, basically. So I mean, that's some kind of argument. So we're getting more Atlantic inflow, and the anticyclonic circulation in the Canada Arctic is becoming much weaker, basically, and much more localized. That's some kind of general pattern.
So that would be driven by the wind pattern.
I suspect so. Yeah.
So that could be enough pattern.
Yeah. Could be. Yeah.
Okay, thanks again.